let's go for the last talk of this session. We have Alex here with us, who is going to talk about FrodoPIR, and I'm giving the scene to him.
Okay, can you hear me? Yeah. Okay, yeah, thank you for the introduction. I'm Alex Davidson, so I'm going to be talking about some work on private information retrieval on a scheme that we build called FrodoPIR. So this is joint work with Gonzalo Pestana and Sofia Selig. So one thing I do a lot is I read Wikipedia articles, and what I typically do is I kind of read through them and then I start clicking links, and before I know it, I've ended up somewhere where I didn't possibly predict I would end up at the start. So something I've realized over time is that actually these kind of signals to Wikipedia can kind of reveal things about, your innate personality and your preferences. And one thing that I might prefer is if, I don't maybe mind that Wikipedia know that I'm browsing Wikipedia, but maybe I hide the pages that I'm looking at. One easy way that I could get around this is just downloading the whole of Wikipedia to my device and just locally, reading it on my device. But obviously, if I have a mobile device where I'm doing it, on any small device, then that's going to be difficult. So PIR is developed not just for this application, but for many other things. But this is kind of the application that PIR looks at. So you have a server with a public database, and you have clients like A, B, and C, and they want to retrieve things from the database. And the thing that you want to hide is the things that the client's trying to access. So we're going to be looking at PIR for indices, which means the database is like a flat array. And each client is going to ask for essentially an index of the database, and they're going to receive back from the database the element associated with that index. And like I said, the thing that's protected is the indices in these queries. So PIR has been around for nearly 3 decades. And there's this seminal work by Kushilevitz and Ostrovsky that kind of showed you can build PIR really easily from additively homomorphic encryption. What you do is you have a client that has a vector of bits, which is the same length as the number of elements in the database. And the ith bit is set to 1, and the rest of the bits are set to 0. And what the client does is they encrypt their whole vector, they send it to the server, and the server has this vector of just all the database elements in their database. So due to the additively homomorphic properties of this scheme, the server can do an inner product between these 2 vectors and essentially get out an encryption of the database element the client wants. They send that back to the client, and the client can decrypt it and learn that database element. So this is all well and good, but you have this problem that asymptotically this is linear in the number of elements in the database, both from a computation perspective and from bandwidth perspective. And essentially, I don't want to denigrate the kind of work that's gone on since then, but really, PIR is kind of still focused on this, how you build schemes kind of in this manner. But what has happened is that various really good papers have shown that using FHE rather than AHE, you can use some more of the capabilities available to you in the FHE schemes, like the multiplications and things, to reduce these complexities down to sublinear things. So one thing to note is that this is usually an amortized complexity. You require the clients to make square root n queries, which may or may not be realistic. And these particular optimizations in modern schemes use this offline-online model where the client and server get together and do something in an offline phase, which makes things more efficient in the online phase. And typically these schemes require low-level optimizations to kind of the FHE libraries in order to make this work, and also kind of the ring learning with errors structure that these FHE schemes typically use as their underlying security assumption. So when I and my co-authors were kind of starting out on this project, we were actually just looking to use PIR for certain applications, and we couldn't really get anything to work. So one of the things that we noticed about these offline-online models is that the clients and the server have to do this protocol in the offline phase between each client, so it's client-dependent. And actually, if you have a server that's kind of constrained by its resources, if you're running something on AWS, if you move things to an offline model, it doesn't actually reduce the cost at all, because you still have to run the offline phase at some point. It just makes the online phase for the client faster. But if you're constrained by like financial type things, then it's not actually going to help. And so what we wanted was kind of like a PIR with pre-processing scheme, where the server can do something expensive, but itself with client independently, and then the clients can just download that so that there's no like interaction between each client and the server in this offline phase. So then you amortize away the server offline computation across all of the clients that access this scheme. And then, so I can't really speak for Sophia and Gonzalo, but I'm not like an FHE expert, and we found that the libraries that were available weren't like necessarily ready to be used for like applications. Like you couldn't just like run it and get it to work. So we kind of had to implement this ourselves, and we didn't really want to get into like the minutiae of how to optimize FHE libraries or Ring LWE. So we wanted something that was configurable and efficient, but that we could implement as fairly limited programmers. So one of the things, so essentially our findings in this work was essentially like, let's try and move back to the standard learning with errors assumption. And the reason we do that is because we can do everything in an integer mod q ring, and q is typically something quite small, like 2 to the 32. And actually we just go back to simple regev encryption, which is this scheme from 2005 and is like one of the first like post-quantum cryptographic public key encryption schemes, and it happens to be linearly homomorphic. And the idea here is we kind of like remove the dependency on polynomial rings, which is something we didn't really want to get involved with, and like hence the name that's fairly contrived. And actually our scheme, along the way, we developed like this ability to develop, to run this pre-processing phase that's completely client independent. And essentially what we have is that the server produces like an amortizable digest of the database that the clients can learn. And concretely, our scheme performs, we think, fairly well. So for achieving a 1 kilobyte database element from a million entry database, it takes less than a second and like fewer than 4 kilobytes of data. And the whole arithmetic implementation of this scheme, you just use a standard unsigned 32-bit integer operations, and only 735 lines of code. And I know lines of code aren't necessarily like a scientific measure, but we thought that was fairly good going for a PIR scheme. So one thing to note before I go any further is that there was concurrent work by Hensinger, Hong, Corrigan, Gibbs, Mekeljohn, and Vaikuntanathan, and they build a selection of PIR schemes, and one of their PIR schemes is mathematically almost equivalent to our scheme. Their scheme went to Usenix, and their paper is very good, and if you're interested in this work, then you should also read that paper. And now I'm going to try and keep this as lightweight as possible, because I know that I'm standing between everyone and kind of the end of the conference. But here are some diagrams. So we have a database, and in each row of the database, we have an element. And the key kind of thing to note about the offline phase is that obviously the client can't just download the database, because that would violate the PIR efficiency criterion. So what the server does is they sample this matrix A, and matrix A has a particular structure, it's pseudo-random, and each entry is like a mod Q element. But don't worry yourselves too much about the mathematics. What's important is more like the dimensions. So when you multiply A, which is kind of short, with the database, which is kind of narrow, you end up with M, which is both short and narrow. And then you can set each client downloads this M. One thing I should note is that the database has these rows, and each row entry has like log row bits, and row is something you don't need to worry about as well, but this adds up to the full number of bits in the element, in the database element. So for each query the client wants to run, or in the future, essentially the client creates these two vectors B and C. So if you're a fan of post-quantum cryptography and lattices, then you may notice that this like vector B looks very much like kind of the thing that you create in the learning with errors assumption. We kind of modify a little bit the distributions that the vectors S and E come from. So S is the typical LWE secret, and E is the error. And we use these like uniform ternary distributions in order to sample these things, which is slightly non-standard. But we verified kind of the hardness of our assumption using the Martin Albrecht's lattice estimator. And you also create this vector C. So in the online phase, really, our scheme is like almost identical to this Kuchelewicz-Ostrowski 1997 scheme. So what the client does is you have this vector B, which is your LWE thing, and you simply add like an indicator vector. This X is slightly different from 1, but you can think of it like a 1 in the ith position, so they want to retrieve the ith element from the database, and then they have this vector B tilde. And the security of this scheme says when the client sends this to the server, the the server can't distinguish this from random based on the security of the LWE assumption. So in the server response, all they do is literally multiply this vector with their database, and they get some C tilde out, and they return this to the client. And then the client outputs the correct database element by doing this kind of like rounding function, and this rounding function returns the database element. And this kind of looks opaque, so I'm going to try and explain it a little bit. And what this rounding function is doing, you can kind of, if you're familiar with this kind of cryptography, it's kind of like this learning with rounding type scenario. But what you're trying to do is extract the width of the matrix times log row bits, and that will give you the row that you're after. And actually, what I'm going to show you is that the row of the database is encoded in the most significant bits of this entry. So if we expand this equation down a little bit, you end up with something in this last row where you have this S multiplied by M, which cancels out on both sides, and all you're left with is the row of the database plus like this error vector multiplied with the database itself. And so here, what this rounding function is trying to do is remove this error, because if you can round, if this error goes away, then you have the database. And what we show in our paper is actually, given the distribution that we sample E from, and given the dimensions of the database and kind of the L2 norm of the growth of this noise, this E times the database is going to be encoded in all the bits except for these most significant bits that we care about. So when we run this rounding extracts the most significant bits, and that, with all but negligible probability, is the database element itself. So that's the scheme. We think it's fairly simple, but obviously, you know, there are things to do with like noise and things which you have to manage. One thing to know about this scheme, it is simple, but it has limitations. So the database itself influences obviously the size of the client upload and the size of the client download. So we choose a tall database, and I'll get into that in a little bit, but that makes the client query, the client upload, fairly large. You could rebalance this by kind of cutting the database in half and putting like kind of the bottom half next to the other half, and then when you make queries, you get two things back rather than one thing. And this will make the download larger, but it will make the upload smaller. But really, this is perfectly balanced when you have a database that's square, so you have root m by root m, root m rows by root m columns. So now, just to kind of go into some like concrete numbers. So these top two charts are kind of like the server's offline and online computation. So in this top left, we're trying to illustrate here. We're comparing here with two schemes that you know, are similar in nature. So this stateful onion PIR and private stateful information retrieval. So on the top left, you can see that actually FrodoPIR in general has a very expensive offline phase, but actually this stateful onion PIR requires like client-dependent offline computation. So when you amortize this FrodoPIR line effectively for like even 1,000 clients, you end up with something that's almost zero. Whereas the stateful onion PIR, you're going to have that cost for every client. For the online phase, again, FrodoPIR is kind of similar to this stateful onion PIR scheme, and there's provided as kind of like a base level comparison, this private stateful information retrieval, which is actually a lot cheaper in the online phase. But the thing to note about this scheme is that it streams the entire database from the server to the client in the offline phase, which I feel, in my opinion, is a violation of the PIR efficiency criterion. But it's there as a base comparison with kind of how fast things can go if you stream the entire database. In the bottom, we focus more on financial costs, which are dictated by Amazon. So again, whether it's a scientific measure or not is debatable. But in the offline phase, what we're trying to illustrate is that things amortize quite nicely as you increase the number of clients for FrodoPIR. And in the online phase, when you combine all of these factors together, the server's costs are much lower in FrodoPIR, even compared with private stateful information retrieval, and that's because of this streaming that they do in the offline phase. For the client, the things mainly to note are that the download is very efficient as compared to previous schemes in both the offline and the online phase. This is like a logarithmic scale, but for context, like FrodoPIR's offline download, so this digest that they download is kind of like around 6 megabytes for a database. So for a database that has like 1 million entries with 1 kilobyte, which is like a gigabyte in size. The client query is not so good, and this relates to this balancing thing. And the reason that we have this client query which is much larger than these other schemes is because if you focus on financial costs, AWS has this particular feature where upload is free and download is not. And so if you put all of the cost in the upload, you kind of minimize all the financial costs. And this is why kind of like using AWS costs as a scientific measure is kind of interesting. But equally, if you do care about financial costs, then this is how you get around it. So on the whole, we thought this was a fairly cost-effective and simple PIR scheme where it fit our kind of applications. We hoped that it could be useful in other applications as well. The paper is on ePrint and the code is on GitHub. In future work, we would like to try and look at more natural queries, so moving away from this index-based PIR and looking at more like making queries to a key value map. And also maybe looking at privacy guarantees for the server database because the database is assumed to be public in this work. So yeah, thank you for listening.
Thanks, Alex. Since okay.
Okay, thank you for the talk. I was wondering why you use this ternary distribution for the error and the secret key, while I think I'm not an expert, but usually it's the Gaussian.
Yes.
And in related work, they use the Gaussian, I think. So I wonder also if this has an impact on performances.
Yes, yes, it does. So yeah, you're totally correct. In this other paper, they use a like more standard assumption where the S and the E are sampled from a Gaussian distribution with a particularly chosen standard deviation. The reason we did this was to try and, because when you do this B tilde multiplied by the database, if you have something that's sampled from a slightly wider distribution than is ternary, then clearly the noise is going to grow. And then therefore, when you do this rounding, you have to make the parameters all work. And this row that I kind of glossed over is relative to, is the number of plaintext bits you can fit in each entry of the matrix. But when you have more noise, you effectively have to reduce the number of, and that makes the database wider, which increases communication, increases computation. And so the reason we were quite risky, if you like to say, with these distributions is because we wanted to try and get as much performance out of this as possible. And then we pay for that by having this matrix A as a bigger dimension. So their work has like a 2 to the 10, n equals 2 to the 10, I think, which is quite standard for like LWE parameterization, whereas ours is like 1,200 or something. And that was to make the lattice estimations all work out. And we felt like, because this A is derived from the pseudorandom seed, which you can give to the client, and the client derives it in this pre-processing phase, that was, more palatable for our costs than making the online computation communication bigger. But equally, you could have a version of our scheme where you sample these from Gaussian distributions. You would just need to modify the row that you use. I think there's a question.
Thank you for the talk. In your evaluation, what was the size for the size of the element, and does it have an impact on the overall performance?
Yeah. So for our evaluation, we assumed everything was 1 kilobyte, but it does have an impact because the database width is essentially the size of these elements. So in the online phase, you're just doing this matrix multiplication per column, and all these times are like single threads. So you have to wait until you've gone through the entire set of columns. So if you go to 2 kilobytes, you're going to double the computation time. Clearly, if you parallelize things, it's not going to be as you might see not necessarily a double increase, but yeah, like the online phase is highly dependent on the size of these elements. I think there's a question here.
I wanted to ask if when you're changing the distribution, doesn't this have some implications on the security of the results? Like, doesn't this lead to like being able to manipulate the results or see which bits of the results are actually changing?
Are you referring to the distributions?
Yeah, yeah.
So if we change, the question is, if we change those distributions, does it impact the security of the...
Exactly.
It does, yeah, because effectively when you change the distributions like this, you effectively use like a non-standard LWE assumption, because the LWE assumption derives its hardness from like lattice problems when you use particular distributions. So if you use Gaussian distributions, you have like worst case hardness related to the cost of like breaking like known hard lattice problems. Whereas if you change distributions like this, then you lose those reductions. But and that's totally valid comment. And so here you could think of this as kind of like the ternary LWE assumption. And there is actually prior art that does this kind of thing, is particularly in N-true-based schemes. If you refer to those N-true schemes in like the LWE world, that many of these schemes actually have this same distribution. So we were relying on that previous work, and we were also relying on kind of the concrete lattice estimator to give us like an idea of how secure these things are. But yeah, you're totally right.
Thanks, Alex. Now we are out of time, and I need to ask you to take questions offline. And we are getting to the closing ceremony, and thanks for being here with us.